Hello, I am the morose Mr. Daycock, and today I'm going to be teaching you about mathematical induction. And I'm going to be teaching you mathematical induction through the use of my friendly robot here. So, my friendly robot has a couple of rules. Well, specifically one rule. He makes a copy of himself. The robot makes a copy of itself, and it makes exactly one. Always makes exactly one. But that one is then the robot, and so that robot makes a copy of itself. So this here follows a very, very simple process. Specifically, the robot makes a copy of itself. And then that robot there, that makes a copy of itself. And then that one, that new one over here, that makes a copy of itself. And that makes a copy of itself. And that makes a copy of itself. Each robot only ever makes one copy, but it always makes a copy of itself over and over and over again. And so the ultimate effect is that these robots will just keep on reproducing forever. Not the first one. The first one won't. We're not going to get exponential growth here. This is entirely linear. It's just one by one by one by one. But ultimately, if this is left to carry on, we're just going to get infinite many robots. The whole world is going to get covered in robots. And so the question is, why isn't the world covered in robots? And the answer is incredibly simple. It's because we don't have a robot that just copies itself and then that one makes a copy of itself and so on and so forth. Even though that's what these theoretical robots can do, we don't have one in the first place. And those there are the two key rules of mathematical induction. One, prove it exists at all. If the thing doesn't ever exist, then it doesn't exist. You can't use induction unless it exists somewhere. And the two, which is kind of the inductive part, prove that if it's true for one, then it is true for the next one. And that is the robot making a copy of itself. What you're basically saying is, I'm going to say, let's say it's true for 3. So maybe I know that it's true for 3. And I know that if it's true for some k, then it is also true for k plus 1. So I've got a tick for k implies a tick for k plus 1. And I know it's true for 3. Well, those two things together tell me that it's true for 4. And then those two things together tell me it's true for 5. And then I know that if it's true for 5, it must be true for 6. And these are the robots reproducing. Each robot makes the next one. Or in this case, each fact makes the next fact, makes it true for the next number. And that is mathematical induction in its essence. The very key thing, prove that it's true once, anywhere, and then prove that if it's true for one, it's true for the next one. Now, I do say anywhere, and that is true. You can start at 17, you can prove it true for 17 first. And then, But the problem is that if you do that, you won't know if it's true for 16. You'll only know that it's true for 18. Because mathematical induction gives us the next robot. It doesn't give us the robot before. So where we always want to always start at 1 or 0. Usually 1, but sometimes 0. We always want to start at the beginning so that we not only know that's true for the start, but we get everything after that. And also, these tend to be the easiest cases to prove anyway. Okay, mathematical induction is always broken down into 4 steps. So let's go through those steps now with a lovely example. Prove by induction that the summation of 2r minus 1 from r equals 1 all the way up to n is n squared. And this is equivalent to saying the sum of the odd numbers is equal to that squared. So is equal to the square numbers. So what it's saying is 1 plus 3 does equal 4. 1 plus 3 plus 5 equals 9, and so on. The sum of the odd numbers are square numbers, and this is true. So that's quite nice. But proving it by mathematical induction, we need to follow those steps. So first of all, and this is step 1, base case. We want to test n equals 1. We want it to be true for at least once. So we're going to test n equals 1. And we're going to test it on each side. So we've got the left-hand side. That means we're going for the sum from r equals 1. We're substituting the n for 1 to 1 of 2r minus 1. But the sum from 1 to 1 is just one term. It's the term when r is 1. So it's 2 lots of 1 minus 1, which is 2 minus 1, which is 1. Okay? Now that doesn't prove anything. We need to show that the right-hand side is also 1. So the right-hand side, well, right-hand side is just n squared. So we're looking at 1 squared, which is also 1. And we have both are 1. So the left-hand side is equal to the right-hand side. So claim true for n equals 1. And this is our first robot. We've proven the base case, so we've proven it's true at all. Okay. Now, our next step. We want to assume that it's true for some k. So this is our assumption. Assume it's true for some n equal to k. And we call it an assumption. We're calling it assumption because we're not saying what k is. But it's ultimately not really an assumption because we definitely do know it's true for some k. We've just proven it's true for some k. When k is 1, it is true. So it's an assumption in a very logical, pure sense rather than your everyday sense of assuming something. So we're assuming it's true for some n equal to k, which it is. It's true for n equals 1, but we're using k because we want this to work for every number. So we want it to be, it doesn't matter what k is. So if k is 3, we want to show that it proves 4. If k is 17, we want to prove 18. And then we want to stay out of the rule. So that tells us that the sum from r equals 1 to k, because remember our n is k now, of 2r minus 1 is equal to k squared. So the distinction here is n is a variable. K is a specific constant that we haven't decided. So there is a subtle difference there between the n and the k, and there's a reason why we're using different letters. Now, part 3 is the work, as it were. This is where we have to actually do the proof. This is the inductive step. And the inductive step is we need to show we need that if true for n equals k, then true for n equals k plus 1. And using our assumption, this is actually not too bad because we already have the information that it's true for n equals k. But the key thing is, when we're doing this, we're going to use that information. We're going to use the information given here in the proof. And we're going to have to do that because otherwise we aren't proving that the next one is true from the previous one. So to prove that it's true for n equals k plus 1, we're going to consider that. So we're going to write down the sum from r equals 1 to k plus 1, because we want the k plus 1, of 2r minus 1. But we can't say that is equal to k plus 1 squared. We cannot say that because that's what we need to prove. We have that if we sum to k, it's equal to k squared, but we need to prove that. So we have to actually treat this as a different thing. Now, there is a rule, a very simple rule from addition. The whole idea here is this is adding everything up. And the sum of all, let's say I've got to add up 1 plus 2 plus 3, dot, 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 plus 9 plus 10 plus 11. Well, that's the same as adding up everything to 10 and then adding 11 at the end. It seems like a very weird, distinct point to make, but what this means in terms of our summation notation is that if we have the sum from r equals 1 to k plus 1 of any function of r is always equal to the sum from r equals 1 to just k of that same function plus the function at k plus 1, because it's just adding on the end bit as well. And this is really, really important. This is in fact exactly the rule that we're going to be using over and over again for our inductive step. If we're doing induction on summations. If we're doing induction on some other properties, then we might use a different rule. But for summations, we're going to be, the very, very key rule is this. And the reason why it's key is that we know this. We know that part. We know what this is. And in fact, we know what this is. So we can test. Right. So let's do that here. The sum from r equals 1 to k plus 1 of 2r minus 1, well, that's the sum from r equals 1 to k of 2r minus 1 plus the function at k plus 1, i.e. replacing the r here with k plus 1. So plus 2 lots of k plus 1 minus 1. And so that's equal to the summation from r equals 1 to k of 2r minus 1 plus expanding and simplifying 2k plus 1. But, and this is really, really important, we know this. This here is equal to k squared by assumption. So that is true to k squared by the assumption step. So this whole thing is equal to k squared plus 2k plus 1. But that factorizes k plus 1, k plus 1, which is equal to k plus 1 squared as required. And notice that we didn't write down that it was equal to k plus 1 squared at the start. What we did was we broke up the summation and then using a bit of algebra showed that it was k plus 1 squared. And then that leaves us to step 4, the conclusion. Don't spell conclusion. So we're going to deal with the conclusion. Okay. Statement true for n equals 1, and if true for n equals k, then also true for n equals k plus 1. Therefore, statement is true for all integer n with n greater than 0. And notice it's only true for greater than 0 because we started with n equals to 1. If we started for n equals to 2, it would have to be n greater than 1. If we started for or greater than equal to 2, if you prefer. We have to think about where we start. And that's it. Those are your 4 steps for mathematical induction. Your base case, prove that it is true for n equals 1, test each side and show they're the same. Your assumption step, which means we just need to say, hey, we know it's true somewhere, let's write that out as in an arbitrary sense. The inductive step, using the assumption. Remember, we used the assumption here, and we used the assumption here. Using the assumption step, proving that the rule is true for k plus 1. Remember, never assuming it's true for k plus 1. Using the truth of it, the fact it's true for k, to prove that it's true for k plus 1. And then lastly, writing all of the information out as a conclusion. Basically writing down, we have a robot, and that robot makes another robot. But in mathematical sense. Right, and that's it. That's everything for mathematical induction, the basic principle of it. Next time I'll be going through using induction for divisibility rules and then matrices. Thank you for watching, and I'll see you in the next video.